Hello, everybody, and welcome to We Measure the World, a podcast produced by scientists for scientists.
But what, from the society point of view, sometimes we not just focus on one landslide, we focus on the region. We focus on the likelihood of a particular area, whether there will be a landslide or not. So the challenge is how we can expand that from the single monitoring site to a region for those isolated ones. So that become one of the very challenging ones. So I think I'm looking forward is basically to develop some kind of upscale method to be able to predict a region or a watershed. That way we'll be much better prepared.
That's just a small taste of what we have in store for you today. We Measure the World explores interesting environmental research trends, how scientists are solving research issues, and what tools are helping them better understand measurements across the entire soil-plant atmosphere continuum. Today's guest is Dr. Ning Liu. Ning Liu is a professor of civil and environmental engineering at the Colorado School of Mines. He obtained his bachelor's in geotechnical engineering at Wuhan University of Technology and both his master's and doctorate in civil engineering at Johns Hopkins University. He is well known internationally for his work on stresses in variably saturated porous media, with his primary research interests in seeking common threads among basic soil physical phenomena, including fluid flow, chemical transport, heat transfer, stress, and deformation. And today he's here to talk to us about his work developing an equation to predict instability in shallow slopes and his vision for the future of the study of slope stability. So, Dr. Ning Liu, thanks for being here.
Yeah, thank you. Welcome. Yeah.
So, first of all, we definitely would love to get into, we will get into your talking about your research projects and interests and other things, but we love to start out in wanting to know more about your background and how you got into science in general, soil science, and eventually into civil and geotechnical engineering.
I grew up in China, and I went through the process of Cultural Revolution, and I was very lucky. And when I was a teenager and graduated from high school, and China reopened the door, and after Cultural Revolution, so I went to the college in Wuhan, Wuhan University of Technology. And after that, I don't have too much choice for what I exactly want to study, but I do get involved into the engineering, civil engineering, and geotechnical engineering. So after that, I have an opportunity to come to the United States to start my graduate study in civil engineering, particularly in geotechnical engineering. First get a bachelor degree and then get a PhD degree. And the area I specifically study is how the soil behave mechanically and hydrologically.
Right. Yeah. So as a young man, did you have any interest in soil science or anything along those lines?
Well, I think that, as I just mentioned, that when I was young, I never thought about I would study soil. More maybe relate to this civil engineering, how to build structures both above the ground or underground, but never thought about it. Will get involved into the understanding of the soil.
Right. Yeah. We have several different questions about there are various research projects that you're involved in studying slope stability and landslide monitoring and other things like that, or at least predicting stability or instability of slopes. You have a couple different projects that you've worked on here in the United States and in Colorado and here in Washington State. I was wondering if you could take us through those different research projects. Do you see them as one whole project? Were they kind of looking at similar questions, or were they completely different, the one in Colorado versus the one in Washington State?
I think it's at the large, it's the big questions, the same question. Basically, when you have a rainfall, whether it's by the liquid, which you call a rainfall, or snowfall, and you eventually, those water will go into the soil, and that instability will occur.
Right.
So both in Washington, where you most have a water rainfall condition, while in Colorado, we have a snowfall, but snowfall eventually will melt. But it all focuses on how the soil is going to respond. The slope is going to respond to those conditions.
Right, right. So let's talk about the project in Colorado first. So you're now at the Colorado School of Mines, and so this study we're looking at along the I-70 corridor there in Colorado. What was the setup of your project, and what was kind of the main, I guess, hypotheses that you were testing there?
Yeah. So in Colorado, we have this one interstate called I-70, Interstate 70, which is the one that cross the continental divide in Colorado. In fact, it's the major highway across the U.S. in the middle part of the United States. And one of the challenges is we have a landslide occur in the high elevation after snow melt in springtime, because snow can fall and accumulate for a couple meters, and eventually in the spring it will melt in within a couple weeks.
Right.
And so that poses challenge for the I-70. For years, since I-70 was built, the cross the continental divide called Eisenhower Tunnel, and right on the western slope, about a couple miles there was a huge landslide body. So when they dig the tunnel, they clean the landslide body, part of that, but then they put all the remaining of drill bit of the tunnel into the slope and build a segment about 1.5 mile. And that become very problematic. Initially, no problem, but after a while, the highway start to settle. And they settle in a very vigorous way. In the springtime, it will accelerate that, but then it will slow down. By the fall, it will stop,
right.
And then come back next year. So for years, since 1970, there has been this kind of settlement, and as a result, it's quite a bit of a settlement. So there are worries about people, and everybody will actually, if you drive eastbound of the I-70, you can feel very bumpy on that road, and it's because of the landslide. So the concern that here is two of them. One is in the short term, it's very unsafe. Right. It could have caused some kind of in the long run, maybe some catastrophic can occur.
Right.
So that is a major concern. And very challenging is because the elevation is about 10,000 feet. And in that segment, you don't have any alternative interstate. So interruption or do a reconstruction become very costly.
Right.
So that's where they think that the Colorado Department of Transportation, in particular, they think that this has a lot to do with water. But how the water is going to affect the slope stability is one of the big issues.
Right.
So for that particular issue, I learned over the process what kind of mechanisms are involved, and eventually we get involved. We get some remediation technique to come up from that.
Right. Now, up there, you've talked about the different characteristics there of I-70 across the Continental Divide. Very high elevation. Yeah. Are there any other particular characteristics of, I guess, of the geology or the soil the soil characteristics that are there that contribute to this? You talked about them building the tunnels and clearing away this landslide body, but still there's things that are going on, that potentially contribute to that movement of the soil.
And the answer is yes, mainly because when the snow melt, it actually causes a lot of groundwater level increase rapidly. And our investigation of the course of 10 years, we find that the particularly very serious under the highway. The water table, for example, under the highway within a season can change at 9 meters, raise about 9 meters.
Wow.
And that changes a lot of stress in terms of what we call the effective stress, and that eventually remobilize the existing landslide every year.
Right. And so I would assume that, like you said, every year there's, as that water table, I guess waxes and wanes and fluctuates. Then that definitely would affect the road surface and the underlying soil beneath that. What are some potential ways to mitigate or remediate those effects?
Yeah, so the groundwater is one of the important. The water table change is very important, and people recognize early. They do a typical remediation is to, on the downslope side of the highway, put a lot of so-called horizontal drain. So you drill the hole into the horizontally, tilt a little bit toward the valley direction.
Right.
So that way will naturally drain the excess groundwater. And however, what they find out is that technique is not very effective. So, and they don't know why. And they also try another different kind of mechanism, is try to reduce the weight of the slope by drilling a extensive caisson to remove the soil and then a rock and then replace by some lighter material.
Okay.
However, that technique also does not work. And so our investigation indicated that because the water table raised rapidly under the highway, the water is actually coming from different place than originally think. It's from the upstream of the highway because you have a very large of the slope that have covered by the snow. And when it's melted, because it melts so rapidly and most of the water converges to ground under the highway. So that becomes a part of a major issue. And we investigated through the deformation monitoring multi-years. We also conducted groundwater monitoring on the table. We drill some more extensive borehole to monitor that one. Eventually confirmed our conception.
Right.
And so we also proposed some of the new method, basically to develop a drainage system in the upstream side of the highway that could be effectively reduce the groundwater table rise.
Right. As you're going through in researching and monitoring, what are some of the instrumentation or the measurements that you have going on there?
Yeah, so we put the inclinometer with the Colorado Transportation Department, drill the borehole, the inclinometer basically to measure the soil deformation at a different depth from one borehole, single borehole. And we also measure the groundwater rise and decline, measure the water table. And we also put some sensor to measure the soil moisture because the soil change the moisture can change the weight of the soil material. And we have the information about the precipitation, snowfall from the National Weather Service. So with those information that we conducted investigation.
Right. What were some of the changes? So you talked about the fluctuations of the soils. Maybe just off the top of your head, or what were some of the changes that you saw in the with your inclinometer and with the soil moisture measurements?
Yeah. So the inclinometer basically confirm when at what depth the landslide occur. It happened at the interface of the bedrock and those field material from the drill bit of the I-70 Eisenhower Tunnel.
Right.
So that confirms where that occurred. And the water table basically tell us how much pressure that you're going to generate underground and due to the snow melting.
Right.
Yeah. So those are the very two important information allow us to put into the model to calculate and then confirm the timing and the depth where the landslide can reactivate.
Right. Well, let's move on to talk about your similar research project in Edmonds, outside of Edmonds, Washington. Yeah. They're here in Washington State. Slightly different geology, slightly different climate. So instead of dealing with seasonal snowfall and the snowpack that's melting, that's creating these fluctuations, I'm assuming that there in Edmonds, Washington, you have constant near saturation of sediments and of the soil there. What were the similarities and differences between those two projects there in Colorado and in Washington?
Yeah. So actually, in Colorado, it turned out that eventually it's the failure surface is mostly below the water table, so it's completely saturated. But the water table that just changed the polar pressure. In Edmonds case, it's the opposite. Even though the water table may not be very deep, however, the failure occur in the above the water table.
Okay.
And so what happened is because the El Nino, La Nino change, and you have an excess of precipitation. The slope sitting there over the years, kind of a balance and, with the environment. But with the excess rainfall during the El Nino year, that can change the stress there inside the shallow soil. So what's challenging is for many years, we can understand quite well and characterize quite well how the stress change under saturated condition. However, under unsaturated condition, it is not that straightforward. It has a lot to do with the soil moisture. It also has a lot to do with soil suction. So what I have done is to basically put that two information, the soil moisture and soil suction together, to be able to assess what's the stress change that will cause the landslide.
Right.
Yeah.
And so, so is it similar? So you're talking about soil suction. So then, are you using in other terms? So soil suction is a civil and geotechnical term that's similar to for those in our audience who might recognize water potential or soil water potential.
Right.
Same idea, just different terms. So were you using the same sorts of instrumentation there in Washington as you were in Colorado?
We use quite different. In Washington case, early the U.S. Geological Survey put some kind of instrumentation to measure the monitoring the water table, mainly to focus on the saturated zone. And in unsaturated zone, this is the situation that we'll extensively use soil moisture and soil suction, basically measure the pore pressure. Under the unsaturated condition, the pore pressure become less than the atmospheric. So sometimes people call negative values. So in Edmonds' case, we extensively measure the precipitation record nearby, and as well as the soil profile of the moisture and suction change. And that become the one defining variables that we can use to forecast or analyze the landslide.
Right. And that's what I was going to ask you. I mean, I shouldn't say it's easy, but after the fact, when a landslide occurs, then yes, you can analyze and kind of work backwards to see what happened, where are those points of failure.
Yeah.
It's another thing to forecast. I guess maybe moving forward in this, what have you learned that might be applicable to better forecasting landslide or slope failures?
Yeah. So in Edmonds' case, actually, it's very important for my career because at that point, we know a lot about the suction and the soil moisture. How the suction and moisture will turn into stress that will change the landscape stability is one of the big questions. So I developed some theory, but never put into work. And so in Edmonds' case, the monitoring give us the record all the way to landslide occur. We are very lucky that our station are all gone because the landslide. But the lucky part because we have all the data up to the moment of landslide.
Right. Yeah.
Right. So that's very unusual. And I remember that one day my USGS colleague called me, said, Ning, your theory work. And he said, I used the moisture record, the suction record, and use a simple equation, calculate exactly the depth and the timing of our observed landslide.
Interesting.
So that gave me a lot of confidence about the theory I built for that. Moving forward, the framework basically now can equally use for any other place. The reason is no matter how complicated of geologically or the slope angles of your material is, what caused landslide is a simply matter of the driving force versus the resistance force. When the driving force exceed or equal to your resistance force, and the slope will give up. So from that point of view, in the framework I have built is basically say, under unsaturated condition, what is the driving force? What is the resistance force? Those are very different than the saturated condition. Those are require us to use the soil moisture, use the soil suction to quantify that.
Right. So I actually let's dig into that, because as part of this, you talked about the theory, you've talked about now you've experienced this, and this has kind of led you into creating these mathematical models to describe and potentially predict slope stability and slope failure. Can you go into a little bit more detail about your these equations that you're trying to create here and that you're working on.
So physically, if you have a soil, the soil can be a liquid, a solid, and air in general under unsaturated condition. If your soil only have a water, basically all the void occupied by water, and what makes the soil become a material to resist the driving force is the skeleton. The stress in the skeleton we call effective stress.
Right.
Under saturated condition, that could be quite straightforward. If you measure the pore pressure, and you will know the overburden of the total stress, you subtract the pore pressure from the total stress, you get effective stress or skeleton stress. Under unsaturated condition, that becomes challenging because you no longer can use the pore pressure or the suction as a stress to remove from. As a matter of fact, when soil under unsaturated condition, because the development of capillarity, because of the development of absorption, the soil actually, the effective stress become higher, which means more stable. However, when the rainfall comes, you resaturate or you go to the wetting direction, it actually reduces the magnitude of that stress. So that the slope become vulnerable and eventually fail.
Right. Now with that I guess I'm just trying to think of the various variables and parameters that might go into a model like that.
Right.
You've explained it very simply. I'm assuming that there's much more detail that goes into that. How does I guess I was thinking slope angle, or how does the soil characteristics play into this model there?
Yeah, so slope angle is the one that provide the driving force because the steeper that you have the slope, the higher that you have a total stress. So that provide, if I said that if you analyze a slope, whether stable or not, you just look at the driving force and resistance force. The driving force is the soil self-weight, and the resistance force is the material property. Sometimes we call soil's cohesion, friction angle, the internally. To resist those driving force, and on top of that one is what make the resistant force is this additional due to the soil's suction, due to the soil's moisture content, and they actually become part of that to be the effective stress to resist that one. And that is why when you have a water content change, you suction change. You change that stress. In my term, called suction stress, which is basically replacement of suction of the water pressure under saturated condition. So when that quantity change or reduce specifically to certain threshold, and your resistance force no longer be able to sustain for the driving force and the slope failure.
Right. Yeah. So what are the next steps? I assume that you're not just going to sit on your laurels but that you're going to move forward and try to. Is there room for improvement with this model, or are you moving on to other things? I guess what do you see as the future of this current research that you're working on?
Yeah. So we have been. I've been working with the U.S. Geological Survey in Golden, Colorado, which is on our campus, and over the last 20 years we have developed many of the sites in the United States. In the East Coast, we have a North Carolina site because that's where the hotspot for the hurricanes. And also due to precipitation. In Colorado, we just mentioned that. And then the West Coast, we have extensive from Washington to Oregon and to Northern California and Southern California. As a monitoring project, the monitoring will give us all the detailed information, both the space and time, how the moisture suction and then suction stress are going to change. And moving forward, those are basically provide some kind of a validation point to continue to refine the theory or to back about the framework. But from the society point of view, sometimes we not just focus on one landslide, we focus on the region. We focus on the likelihood of a particular area, whether there will be a landslide or not. So the challenge is how we can expand that from the single monitoring site to a region for those isolated ones. So that become one of the very challenging ones. So I think I'm looking forward is basically to develop some kind of upscale method to be able to predict a region or a watershed. That way we'll be much better prepared.
Right. Definitely something, especially like you mentioned down in North Carolina. I mean, you've talked about dealing in snowfall, mountain ranges in rainy climates in the Pacific Northwest. But that was another one that maybe in the future we'll get to talk about North Carolina or dealing with monitoring those kind of issues with her.
San Francisco Bay is another area where the population and the landscape intersect.
That's the other thing. I mean, the intersection. I guess this kind of gets into the the human geography of it all as well, and how of course there's going to be human impact with these landslides. I guess the closer they are to human occupations and those kinds of things. If they're landslides out in the middle of nowhere, it doesn't matter too much. But definitely if we're dealing with landslides there on I-70, or if we've got landslides due to hurricanes in North Carolina, or especially as we've seen in California along the Pacific coast there, where you have that potential arid environment that then gets inundated, and you have lots of people living in hills or along slope sides. You've got lots of highways, freeways, and other things that are there that then get impacted. And so any type of, I guess, monitoring or prediction, slope stability or slope failure prediction would go a long way to minimize the human toll or the impact there as well. What are some current challenges that you have faced in trying to just, I guess, simply characterize soils within geotechnical engineering? And are there ways that we can, make those measurements or those characterizations better, in your opinion?
In terms of what? In terms of landslide prediction, or in terms of how we can better understanding the soil behavior, hydrological, mechanical? What?
Yeah, so I mean, let's talk about the first just in general terms, and then maybe we can talk about the landslides in more specifically.
Okay, yeah. So I think the measurement of soil moisture, it's a technology that has been, in my view, quite to the degree that we can feel quite confident to understand the soil moisture. But the suction is not so. Soil suction remaining still very challenging, particularly in the field condition. For now, we only have a direct method called tensiometer. That only gives us the suction range in a few hundred kilopascal. However, in nature, the suction can vary very over 6 order magnitude, everything from 0 to gigapascals order.
Right.
So the sensor is in that aspect is somewhat limited. Many of the phenomena could probably require much more wider to be able to characterize the soil condition or suctions.
Right.
So that's one of the areas that I think that remain can be improved. Doing that would greatly improve the ability to monitoring slope and provide. The other thing is because Mother Nature are complicated, none of the two slopes are the same.
Right.
So providing some kind of forecasting, early warning system, it becomes more challenging. However, we have a developer in different disciplines, different kind of technique or methods to cope for that. For example, we have a much better idea now about the remote sensing to know the topographic, and the topographic can provide a very powerful information, the geological material from remote sensing, and that provide a very good about the history of those particular area.
Right.
And those information probably can also be used to forecast landslide.
Right. Right.
So there are some of the areas. These are some of the things I think that can do better job.
Okay.
In the future.
All right. I guess I should have maybe asked this a little bit earlier, but you'd mentioned talking about effective stress as kind of being a center point for your research. When did you move, or when did you first decide you wanted to get involved in exploring this concept of effective stress?
Yeah, in 1993, I moved from Washington, D.C. area to Colorado. And so that is actually the first time I start to expose of swelling soils and slope stability issue. Before that, I have some limited exposure to unsaturated underground nuclear isolation. So it really, the issue about the slope stability, the issue about how the soil can swell, cause the damage to civilian and residential house. It's the one of the turning point, I would say, that for me to start to look at more serious about the effective stress.
Right.
Because those, both of the cases I just mentioned, swelling soil, slow stability, in many cases that occur under partial saturated condition.
Right.
So that requires extensive knowledge about how we can develop effective stress, which has been very much limited on the conservative side, limited to saturated soil condition. But in reality, many of the infrastructure is under partially saturated condition.
Right.
So that's the turning point back to 1990.
Right.
So I started to pursue that.
Okay. Yeah. All right. In talking about being able to monitor, it's there are a lot of these projects for various municipalities or local or state governments might be a bit more cost prohibitive to be able to install monitoring stations all over the place, like we would prefer, right? I guess it just kind of was crossing my mind when you're dealing with these models. Are there primary drivers? Would you say, for instance, that soil suction would be a primary driver? Say, if people wanted to do a simple monitoring solution where installing soil suction sensors or something along those lines, would that be a shortcut, or is it much more involved in when you're dealing with monitoring and potential prediction? I think
from my point of view, most of the monitoring is just give us the first hand to develop a predictable theory. And ultimately, the predictive theory should be the variable that very easy to be measured. So from that point of view, and in the future, I don't think every slope can put those sensors there.
Right.
But so we need to develop some kind of easily access information. Of course, the accessibility depends on technology. So for now, let's say I just mentioned that the topographic, the geological material, the vegetation, those information could be handily obtained for most of the region and with the high resolution. If you have a technique of remote sensing. So eventually, and the precipitation also too, the climate change somewhat predictable in a way, at least to the short term, middle term. So eventually, I think will be the ultimate goal is to develop the tool or the model or the framework that using those accessible information. And of course, soil suction moisture will still be as a rule as a tool to build those information.
Right. I think that's our time for today. Okay. I've really appreciated the discussion. I know that I've learned a lot. I didn't know a lot about this, and so it's been great to be able to talk with you. So thank you for coming by.
Yeah, thank you for having me.
And if you in the audience have any questions about this topic or want to hear more, feel free to contact us at metergroup.com or reach out to us on Twitter at meter_ENV. And you can also view the full transcript from today in the podcast description. That's all for now. Stay safe, and we'll catch you next time on We Measure the World.